Hey everyone, welcome back. The campus hasn't provided enough spare batteries for the microphone, so my apologies in advance if the microphone runs out of juice and stops working. But today I'm going to talk about ways that statisticians justify the kinds of objective functions that we solve in machine learning and regression. Recall that back around lecture 5, I divided machine learning algorithms into 4 levels. So at the top level, we think of us having the application, which then justifies some model from which we derive an optimization cost function. So the optimization problem that we want to solve. And then we develop optimization algorithms for solving those problems. So the last 2 lectures where I've been talking to you about regression, what I've been talking about is what optimization problems we formulate to fit curves to points, and what algorithms we use to solve those, things like steepest descent, Newton's method, and just using plain old calculus and then solving a linear system of equations. Today, I'm going to go up a step in this hierarchy, and we're going to talk about the model itself. And what we're going to ask today is, what are the reasons why we think it's a good idea to solve some of these optimization problems, like least squares regression or logistic regression? And I will also, when I describe these models, I'll also talk about how they contribute to underfitting or to overfitting. So statisticians sometimes start with a model of reality, what they think they are trying to find out there in the real world, and then builds a procedure that tries to tease out the truth from what we can measure. And so one model you might believe in is that the sample points come from some probability distribution. We don't generally know what that probability distribution is. So the way we write that is that every sample point xi comes from the same distribution d. And so the hope there is that every sample point does come from the same distribution, even if we don't know what that distribution is. And then here's another big leap of faith that does hold in some contexts. We're going to assume that the y values are the sum of some unknown function that we would like to estimate. And just to be clear, this is not a random function. It's completely deterministic. But we're going to assume that when we make a measurement in the real world, there is added noise. So some extra random noise gets added to every observation of a label. And so, for every sample point xi, its label yi is going to be g of xi plus epsilon I, where g is the unknown function that we want to approximate. And one thing that is getting in the way of approximating that function is these little random noises that get added. So we're going to assume that each of those noises also comes from the same distribution, which we'll call d prime. And I'm also going to make one additional assumption for now that's, for this semester that is, that's pretty crucial. We're going to assume that the noise distribution has mean 0. All right, so what we're doing here is we are positing that reality is described by a function g. And we don't know g, but it's not random, it's deterministic. We want to approximate g. And it measures some consistent relationship between x and y that we're going to estimate. But then there's this added noise, which represents measurement errors and other sources of statistical error. The noise is independent of x, so it's the same noise for every sample point. That's kind of a big assumption, not always true in practice, but it's all we have time to deal with this semester. And one thing about this model is that it does not account for systematic errors, where by systematic error I mean, let's suppose you have a measuring device that always adds 1 to the measurement. So every label is 1 greater than it should be, so this error in that case would not have mean 0. The problem with that is that there's no way to diagnose that just by looking at the data alone. So there's nothing we can do about that without other measurements or other external input. So that's why we're assuming that d prime has mean 0, because if it doesn't, we'll never know. All right, so the goal of regression, of course, is to approximate g, estimate g. And so I'm going to use h for hypothesis to refer to the function that we build to estimate g. The ideal approach here is if we could somehow choose our hypothesis at any given test point x to be an expectation over all possible noises of the label given a data point x. And so essentially you take this function here, and we're taking the expectation of that at a specific point x, and well, g is not random, so the expected value of gx is gx. Epsilon I is random, so we're adding the expected value of that noise epsilon, and we've already decided that the mean of that noise is 0. So what this is saying is that if I want to get at gx, a way to do it is to, if you had lots and lots and lots of data that was all exactly at the point x, you could take the average. Well, as a practical matter, we don't get to choose where our data is, so we can't realize this as an algorithm, but this is an ideal that we can strive for statistically. And so let me explain a little bit more what this means. Suppose you have a graph of this function g of x that we're trying to approximate. And then at a specific point x, let's call it x prime, just so it has a different name. Well, what we'd like to do is we'd like to know what the value of g of x prime is, but imagine that you could measure the label at point x 1,000 times. So you measure it once, and because of the added noise, you don't get g of x prime, you get this. You measure it again, you get this. You measure it again, you get this. You measure it again, you get this. Well, maybe these points, these measurements, are in some distribution. So suppose, for instance, they come from a normal distribution. If our noise is normally distributed, that's a sideways normal distribution over those points. Then what we could ideally do is take the expectation of that normal distribution, and that would tell us where gx prime is. Again, this is not something you can do in practice. It's just an ideal that we strive for. And the point here is that if this expectation is defined at all, then that kind of partly justifies our model of reality, that there is some underlying function g that models the relationship between x and y. Any questions about that so far? Mm-hmm.
Sorry, just for the notation, what is the subscript that you use?
Yeah, that's what I was asking myself as I started to write it down. I know this is probably supposed to be something else, but for now, let's make it and call it epsilon. There's probably a better way to write that, but I need to think about that more after class. Sorry. Whatever I decide on, it'll make it into the final version of the lecture notes. Other questions? Yeah. Which unconditional expectation are you looking at? I'm sorry, say that louder. Oh, we are, this has mean 0. Why is it what? It's not conditioned on xi because we're just going to assume that every measurement has the same amount of noise regardless of where x is, which again might not be true in practice, but is the best we can figure out today. Maybe I'm not understanding your question now. Okay, sorry. So with this model in mind, now I want to talk about where does the least squares cost function come from? Why do we optimize this particular function, the sum of squared errors? Well, it actually can be justified from this model if the noise is Gaussian, if you have normally distributed noise added to every label. Then, if we apply the principle of maximum likelihood, as we discussed about a few weeks ago, maximum likelihood is going to tell us that the least squares cost function is the right one to use. All right. So again, our assumption now is that the noise is normally distributed with mean 0 and variance sigma squared. So the label itself for training point xi will be the normal distribution with mean g of xi sigma squared. So to apply, before we apply maximum likelihood, I want to remind you what the normal distribution's PDF's logarithm is. We encountered this before, last time we did log likelihood. But, so, if we take f to be the PDF of this distribution here, and what's the logarithm of that PDF? You get minus yi squared minus mu I, yi minus mu I squared, pardon me, over 2 sigma squared minus something that is a constant and therefore will not matter when we do maximum likelihood. And here, the mu I here is the mean of this distribution here. So it's just g of xi. All right. So now that we remember that, I'm going to go ahead and apply maximum likelihood to fitting a curve to this noise. And so the idea is that I am going to take a curve that I want to fit to this data, and I'm going to use maximum likelihood to ask the question, what are the parameters for this curve that are most likely to have given me the data that I received after adding random noise? All right, so I'm going to jump straight to the log likelihood here. And so I'm asking about the likelihood of g. Now, g is a function. You might be saying to yourself, what is the likelihood of a function? Well, remember that function is based on parameters. So if we're fitting a linear function, then you've got the weight parameters for a linear function. So we're really fitting the parameters of the optimization method, in this case, the regression coefficients. But I'm just going to write g as a shorthand for the parameters of g. And we're given input data, training points x, and labels y. And so the log likelihood of that is the natural logarithm, you'll recall, of the likelihood, which is the product of f of y1, f of y2, f of, and so on. I should probably have a subscript on all these f's because each one has a different mean, but forget about that for now. Just pretend, remember these are all slightly different f's. And so we can rewrite that as a sum, the logarithm of f of y1 plus the logarithm of f of y2. And that, well, now we're going to substitute in this for our PDF. That's going to give us, there's a shared constant, 1 over 2 sigma squared. And then there is the sum over all of the training points of yi minus g of xi squared. And then minus some constant, which still doesn't matter, because we're maximizing the likelihood. All right, so we're doing maximum likelihood estimation. We want to maximize this expression. And when we're maximizing this expression, well, remember, multiplying it by a constant doesn't change the maximum. Adding a constant at the end doesn't change the maximum. So we don't really need to look at those parts very closely. The part we need to look at is this. This is the sum of squared errors objective function. So starting from a Gaussian noise model and applying MLE, what I get out is the conclusion that I really want to optimize that thing in the red box. And also let me point out this minus sign here. What that minus sign means is that maximizing the likelihood is equivalent to minimizing the thing in the red box. So that's how we go to minimizing the sum of squared errors. And so the takeaway here is that if I have Gaussian noise and I apply the principle of maximum likelihood on, well, I'm treating G as a parameter, even though it's a function, which is really made up of many parameters. Applying that principle tells me that I should estimate G by least squares regression. So in other words, MLE is telling us that I should choose G here so that that's minimized. Any questions about that? Yeah. You don't get how we... Oh, well, so the question is, how did I get this takeaway? Basically, when I say least squares regression, I'm saying that. I'm saying minimize that. So that's what that phrase means. And keep in mind that we know the value of yi, we know the value of xi. The only thing that's in that equation that we don't know, that we have to solve for, is g. So that's why I say estimate g. Does that answer your question, or is there more to it? Okay. Sorry if I didn't get to the heart of the issue, but... All right, so one thing to keep in mind is that I have told you in previous lectures that least squares linear regression, one of its flaws is that it's very sensitive to outliers. Now, if we really, truly have Gaussian distributed noise from our real-world measurements, then that sensitivity to outliers is not really a problem. This is the right thing to do. The normal distribution doesn't give you really big outliers very often, so you're going to be okay. However, if your noise really is not normally distributed, if it sometimes just throws in values that are way, way out in left field, then this might not be the right algorithm because it's sensitive to outliers. Was there a question over there? Mm-hmm. G of x of I is the parameters that describe the distribution? Mm-hmm. Mm-hmm. Yeah. So in other words, I think what you're getting at is each of these f's is a PDF of this form. Well, no, sorry, not that form. That's the log of the PDF, but so each log of this function is the PDF of this form. And G, our parameters are hiding inside G. G is just a function, but when I say we optimize G, I really mean we optimize its parameters, whatever those are. And there's a lot of flexibility what those are, but that's what we do. Does that answer your question, or is there more? Okay, cool. Going on to the next brief topic, I want to tell you what the phrase empirical risk means, because it comes up a lot in machine learning. So remember, we've already defined the concept of risk in previous lectures. We can define it in the context of regression as well. If we have a hypothesis H, the risk of that hypothesis is the expected loss. Risk always means expected loss. So here, that's going to be whatever our loss function is over all of the possible points and labels that might be given to us, or in other words, over all pairs, sample point X and label Y, in some joint distribution that we imagine that these things come from. So, as you know, LDA and QDA are techniques where we try to estimate this risk directly. But those are generative models. We can also ask, what about discriminative models like logistic regression? In this case, we don't know that joint distribution of X and Y. We don't know X's distribution either. We don't attempt to estimate them directly. So how can we minimize risk? Well, we define a distribution called the empirical distribution. The empirical distribution, let me be clear, is a discrete distribution. So what we're doing is we're essentially replacing a continuous distribution with a discrete one. Specifically, it is the uniform distribution over the sample points. All right, so what we're doing here is we're taking all the sample points, we're putting them into a hat, we're stirring it well, and then we're picking out a random sample point. That's what the empirical distribution does. It chooses each sample point with equal probability. So again, it's a discrete distribution, not a continuous one. It can only give you one of the sample points you've been fed. Once you've defined the empirical distribution, we can define the empirical risk, which is the expected loss under the empirical distribution. And so it's not hard to see that that is. We'll call it function r hat of h. This is just the mean over all the sample points of their losses. Now, recall that a hat on anything is usually a statistician's way of saying this is an approximation to some other thing r. So indeed, this is an approximation to this. Since we're not building a model of the distribution of x and y, in a discriminative model, this is what we can do to try to estimate the risk. It's like the totally obvious thing to do, but I just want to be clear that it has a name. It is statistically justified by this empirical distribution, that this empirical risk, hopefully, if you have enough sample points, will be a good approximation to the actual risk. And And in the limit, as n goes to infinity, often r hat converges to r. Not always. It depends on how well behaved your distribution is. But it happens in a lot of circumstances. And so we see objective functions like this all the time. This is just the mean loss. And we've seen it several times this semester. This comes up very frequently in the literature, and the effort to minimize this empirical risk is called empirical risk minimization, and it is kind of one of the basic underpinnings of machine learning. It comes up over and over again. There's nothing complicated about it as a concept. It's just, this is our way of thinking about how, as a statistician, we go from what we really want, the true exact risk, to some approximation of the risk. And the main takeaway is just, this is why we usually minimize the sum of loss functions. Nothing really deep, though. Any questions about that? Yeah.
The linear least squares regression, the loss function would be like subtracting them and then squaring it?
For linear least squares regression, yeah, we define the loss to be the squared loss. So then we substitute it for L here. And so, yeah. Mm-hmm. Oh, by the way, one more thing about the empirical distribution. If you take the covariance matrix of the empirical distribution, that is the sample covariance matrix. All right, we're going to do maximum likelihood again one more time. This time, I want to explain, or give one explanation, for where that very bizarre logistic loss comes from. So, another way to phrase this question is, what cost function should we use if we want to interpolate probabilities? So, suppose that you do a regression, and suppose that the behavior of the actual real-world data is that if you are given a point xi, then the probability it is in the class that we're testing for is yi. But when you do logistic regression, you are predicting that label. And so what about our predicted probability? That is h of xi, where h is the hypothesis that we learn. So of course you want hxi to be close to yi. All right, so someone gives you some data. Well, here's the way I think about it. Suppose that each sample point that you're given is duplicated. So we make many copies of the sample point xi. And then we assign each one a label separately using the probability yi. So out of those beta duplicate copies of this point, yi times beta of them are going to be in the class, and 1 minus yi times beta of them are not in the class. Now, the size of beta is not very important, but I want you to just imagine for now that beta is chosen so that these are both integers, so that they actually give you an integer number of copies. So now what we're going to do is we're going to use maximum likelihood estimation to choose the hypothesis that is most likely to generate this particular sequence of sample points and labels. And if you do that, you get the following estimate. So the likelihood of any particular hypothesis, given the data, x and y, well, I'm going to take a product over all n sample points. Inside that product, I'm going to take more products. I'm going to take yi times beta copies of the predicted probability. So in other words, I'm predicting a probability of hxi, and my model is saying, what is the, given my choice of h, what do I believe is the probability that I'll generate yi times beta copies that are all in the class in a row? And then, after finishing that, generate an additional 1 minus yi beta copies that are not in that class. So again, this is based on my estimates of the probability. What's the probability that I go in class, in class, in class, in class, in class, not in class, not in class? So that is the probability. And the log likelihood we'll write it little L of h is, of course, the log of the big L likelihood. And so if you apply the logarithm to this probability here, then the beta comes out, and then you have a sum of the exponents come down So taking the log of that probability gives us this thing. And if you have a good memory for formulae, you might recognize this here, because that's the logistic loss function. Well, it's minus the logistic loss function, so I need to throw a minus sign up front there. So I want to maximize the likelihood. I want to maximize this expression here. As before, the beta is now irrelevant. What actual beta we chose doesn't matter. What matters is we have an expression here that we want to optimize. And there's a minus sign here, which tells us that maximizing the likelihood is equivalent to minimizing the expression in the red box. Now, my main takeaway here is that when we apply the principle of max likelihood to the probability of generating this particular sequence of labels, that is equivalent to minimizing the sum of logistic loss functions. Actually, let me write it that way. So the principle of maximum likelihood is one way to explain where this bizarre looking logistic loss function comes from. Any questions about that? Yeah. Right. So the question is, do you, I presume you mean here, do you need a something choose something else to give you a binomial distribution? So the answer to that question depends on, when I say we are choosing yi beta copies that are in the class and 1 minus yi beta copies that are not in the class, do I mean in that order or do I mean in any order? So if I say I mean it in that order, I want all the, in class, in class, in class, in class, out of class, out of class, then the answer is no, you do not need a constant there. But if the answer is I want to allow it in any order, then yes, you need to add the binomial coefficients to the front of that likelihood. But they're constants. Either way, you get the same answer to the maximum likelihood problem. Yeah, it'll be different from each eye, but it's still a constant. It just doesn't, the thing that we're trying to optimize, remember, the only thing that's not a constant is h. And so throwing a bunch of constants in here, yeah, they're different constant for each eye, but it doesn't affect what the optimal h is. That is a good question, though. I want to shift now to a pretty famous topic. There is something called the bias variance decomposition that everybody who's in machine learning should know about. So the idea here is that we can generally identify two different sources of error in our hypothesis. And one is called bias and one is called variance. So the bias is the error that we experience because the class of hypotheses that we are using just are not a good fit for the data. So in other words, we just can't get an H that fits G well. An example of that would be, well, suppose that G is quadratic and I try to approximate it with a linear approximation. So obviously, if G looks like this, and I try to fit it with a straight line, there's only so much, well, I can't succeed very well. I'm pretty limited in getting a good approximation there. The other obstacle to getting low error and correctly approximating G is called variance, and this is the error because of the fact that we unwittingly try to fit the random noise in the data. So an example of that would be we fit a linear ground truth with a linear hypothesis. And yet, after doing that, well, we should be able to get a perfect fit. If you have a line, you should be able to fit it perfectly with a line, but somehow we don't. Well, typically a reason that happens is because our data are not perfectly lying on the original line G. There's noise. And so the bias variance decomposition gives us a way to actually separate out these two sources of error mathematically. So I'm going to use the same model I introduced at the beginning of the lecture. We have sample points xi that all come from the same distribution d. We have noises, scalar noises, that all come from the same distribution d prime, and the label on each sample point, yi, is equal to g of xi plus epsilon I. Remember also that, again, our errors, our distribution d prime has mean 0, because if it doesn't, there's nothing we can do about that. And we are going to fit a hypothesis, h, to x and y, our data and labels, and we hope that h will look a lot like g. One thing that's sort of interesting when you think about this is we're assuming that x and y are random variables from some joint distribution. And so once you fit your hypothesis h, even if your learning algorithm is deterministic, h is in a sense a random variable because it depends on random x and y. Now, h is a function. Maybe you've never thought of a function as being a random variable before. But what I mean by that is that essentially the function is just defined by its weights. We have some parameterization. We pick some weights. And those weights are a function of x and y. And if x and y are random, then those parameters inherit that randomness. All right, one thing we do in the bias variance decomposition is we consider some arbitrary point. You can think of it as a test point, but it doesn't have to be a test point. It could be a training point, a test point, an arbitrary point. So some point z in your feature space. Again, not generally a sample point, though it can be. Just anywhere in your feature space. And we're also going to imagine, suppose that I have the ability to go out into the real world and take a measurement of the label at point z. And so suppose that that measurement comes out to be gamma. And so gamma is the ground truth function measured at point z plus some noise. And here, again, that noise comes from the same distribution as the noises in our training data. So test data, training data, we assume that both kinds of measurements have the same noise. All right, just to be clear, z is an arbitrary point, but it's not a random point. The label at point z is a random point. because we've added a random error to it. And we're going to need to know the mean and the variance of gamma later on. So let me just point out that the mean of gamma is gz because we're assuming the mean of epsilon is 0. And the variance of gamma is whatever the variance of epsilon is, because gz is not random. All the randomness comes from epsilon in this model. What we're going to do now is we are going to look at the risk function when the loss is the squared error. So this model is, this decomposition is going to be specific to least squares regression. So the risk of a particular hypothesis is the expected value of the loss of our hypothesis, our guess, H, and the label gamma. And this part is very subtle because the question is, what is this expectation over? It's kind of complicated. We're taking this expectation over all possible training sets. X and Y chosen from some joint distribution, and also the values, overall possible values of gamma. All right, so to understand this expectation, let's remember what are the random variables in this. Well, remember we're treating H as a random variable because it's a function of X and Y, so it inherits the randomness from X and Y. Gamma is also a random variable because of the added noise. So we're taking the expectation over all of those things. And so in a sense, we are taking a mean over a probability distribution of hypotheses, which is kind of weird if you've never seen it before. But remember, X and Y come from some specific probability distribution, and therefore the parameters of H also have a distribution, which might be extremely complicated, but it exists. And so we're just going to think about the expectation over that distribution. So now what I'm going to do is I'm going to plug in the squared loss function. So we will assume that our loss here is just the squared error. So that's the hypothesis at arbitrary point z minus the label gamma squared. Let's complete the square. So we can write that as the expected value of hz squared plus the expected value of gamma squared minus 2 times the expected value of gamma times hz. Now at this point we need to observe that these two things are independent of each other. If you're wondering why that is, well, h of z purely depends on the training data, and all of the randomness in gamma is noise introduced into the test error. And the training could have been done even before that test measurement was even made. So those are independent. And so because those are independent, we can separate them out into two different expectations. The other thing I'm going to do now is I'm going to use the standard definition for the variance of Hz and the standard definition for the variance of gamma. And so plugging those in, we get this. So if you're wondering where these terms came from, well, this term here became these two terms here by applying the standard definition of variance. And likewise, this term here turned into these two terms here by the same definition of variance. And lastly, this term became this one because of independence. Now what I'm going to do is I'm going to take the three expectation terms and put them back together into one by uncompleting the square. So I can shorten that a bit by just writing it as the expected value of Hz minus the expected value of gamma, all squared, plus the two variances. And the last step is I'm going to, remember I told you what the expectation and variance of gamma are, so let's plug those two in, and that gets us to our final form. All right. So I've taken the risk, and I've divided it into three different pieces. And those pieces all have names. So the first piece here, this is the squared bias of the method, of the regression method. So the bias itself is just the expected h minus g part, but we get the bias squared here. The second term is called the variance of the method. And the third one, which is sometimes omitted in this calculation, is called the irreducible error. And the first two come from the regression method, and the last one comes from measurements of the test points. So that's why the last one is kind of independent of the others. So now I want to show you some graphs to show you what these formulae, what these expressions actually mean. So let's take a look at this figure. What we're doing here is we're trying to fit a sine wave. So if you look at the left, you'll see there's this sine wave here. That is our ground truth. horizontal axis. You can think of that as the z-axis. All right, so I'm going to fit this sine wave with a straight line. Obviously, a straight line cannot fit this sine wave particularly well, but we'll try anyway. And so what we're seeing on the left is we have generated 50 different fits of straight lines to this sine wave, and here's how we did each fit. We sampled 20 points at random from the sine wave, but the labels all have noise. They all have Gaussian noise. So that's why you get a different line each time you do this. Each time we get 20 different sample points with different labels, and we fit a line to them with least squares linear regression, and those 50 lines have been plotted there in black. So those are basically 50 different versions of our hypothesis, all a little bit different because based on different random data. Now on the right-hand side, you can see we have, what we're doing is we're taking the errors at a particular point, like for instance, suppose I select this point z here, let's call it z prime. So there I've got g of z prime is the true value, but I interpolated with a straight line, so there's h of z prime is my actual guess for what the value is at z. And obviously that guess is not quite right. So we want to take this error here between these 2 points, and we want to break that down into components. And so those components are plotted on the right. The bias first, the variance second, the irreducible error third. And to understand this, look at the red line on the bias graph. That is the average of, if you were to do this regression infinitely many times with infinitely many random sample sets, that would be the average. So this is essentially the expected value of hz. And so now if I look at my point z prime and say, here's g of z, and here's expected value of h of z prime. Then the vertical distance between those 2 points, that's, well, in this case, it's the bias squared. And then the variance. Let's look at the same point, z prime. We can look at in where z prime is on the red line, that is the expected value of our hypothesis. But we don't get the red line, we get one of the black lines. That's the actual hypothesis that we chose this time. And there's an error between those two as well. That's called the variance. Lastly, the bottom graph shows here's z prime, here's the true point, ground truth of z prime on the parabola, but when I sampled the test point and I took a measurement there, the measurement was not exactly right. It was a little bit off because there's noise. And so that's the irreducible error. One thing I should make clear is that sometimes this decomposition is at one specific point z. So what I just showed you was we pick one specific point z, and we do at that point the bias variance decomposition. But it's only natural that you might want to sort of have a summary of the bias and the variance over the entire range of this function. And so another version is you take the mean over all points. Specifically, we assume that our test point z is chosen from the same distribution as the training points. So we think of z now as being a random variable. And then you take the mean over that distribution. Of the squared bias and the variance. And that kind of gives you three numbers that summarize your bias, your variance, and your irreducible error over the entire range of possible test points, rather than at one specific test point. So there's two different versions of this decomposition. Any questions about this so far? Yeah. Why is the noise what? So it's hard to see exactly what's going on in this figure without looking closely at it. But what we're showing you here is that is the blue curve. Now in black, it's the same as the blue curve from the original drawing. But if you actually sample points, if you actually take measurements of that sine wave, you don't get points that lie exactly on the sine wave. So you see now all this sprinkling of points around that sine wave. That represents actual measurements of different test points. Does that answer your question? Yeah. Great. Yeah. Yeah, that assumes that you're doing models on a test set. Though, I mean, if you're not doing that, you can throw away the third part, the irreducible error, and just keep the first two parts. Mm-hmm. Well, I should say this isn't a method, really. This is a statistical way to think about what our machine learning algorithm is doing. I'm not giving you a way to actually calculate these values. The only way you can calculate these values is if you have synthetic data. If you are generating random data on a computer and you know the underlying distributions, then you can actually compute these things. If you're not, you can't. So you can't compute these things on real-world data. What you can do, though, is reason about them, and that's what we're doing.
Okay, so maybe this tool is more durable for us to analyze our models, but it may not be so practical for us.
Yeah, a lot of this is theoretical, but I think, well, what I'm going to do next is just write down a list of consequences of what we've just learned, and I hope that will clarify how this connects with everything we've been learning so far this semester. Yeah.
That's what we just discussed. Mean that this would be a good approach to estimate models like test data on idle computation or whatever.
Would this be a method for estimating?
Yeah, like to understand, like when we actually have the test data and we actually have different models from anyone who participated, can we say that this would be like a good estimation method?
Partly. So the questions about testing and training, and what I'm about to show you is how these things relate to the differences between training error and test error. So this is going to lead us to understand why training error and test error are different from each other, I hope. So, but let me go through the next part and then let me know if this doesn't answer your question. So what I want to do now, again, is write down a list of the consequences of what we have just learned about the bias variance decomposition. So the first thing is when we talk about underfitting, generally that means we have too much bias. Again, remember the example, if you have a parabola and you try to fit it with a straight line, you underfit. Well, now we can actually mathematically quantify what it means to underfit. It's the bias. Overfitting, on the other hand, is when you have too much variance. And so where training and testing come into this now is that when we train, and you look at the training error, it reflects the bias but not the variance. Variance is invisible in your training error. You just don't know it's there. But the test error reflects both the bias and the variance, which is why when we do validation, we often discover that we've been overfitting. And that's why low training error can fool you when you've overfitted. You don't realize from your training error that you have a problem because it just doesn't show the variance. Now, I should say, for many distributions, but not all, getting lots and lots and lots of training data is a good way to make your variance go away. In the limit as the number of sample points goes to infinity, variance ideally will converge to 0. Another thing is if you choose a class of hypotheses that have the capability of fitting the ground truth exactly, for many distributions, meaning pretty much all really well-behaved distributions, the bias also goes to 0 in the limit as n goes to infinity. But if you choose a class of hypotheses that just cannot fit the ground truth, like when you're trying to fit a parabola with a line, then of course failure is built in. There's just nothing you can do to stop the bias from being large. Though I have to have a little caveat here. It's large at most points. And the reason I say at most points, well, remember, there are points where the bias is 0. Wherever the line happens to pass through the sine wave here, the bias is 0. But most points, the bias is not even close to 0. This also has a profound impact on what happens when you add a new feature to your model or remove a feature to your model, from your model. So if you add a good feature, that hopefully will reduce the bias. This is a bit of a circular statement, though, because what is a good feature? It's one that reduces the bias. But if you have if you're trying to fit a quadratic with a line, adding a quadratic feature is going to save you. Also, adding a bad feature, one that has no predictive power, well, it won't reduce the bias, but it generally won't increase it either. I'm going to say it rarely increases the bias, but just to be clear, I do not know a mathematical proof that a feature can't increase the bias. On the other hand, I've never seen a counterexample either, so I don't even actually know whether it's possible or not. However, adding any feature, whether it's a good feature or bad, generally increases the variance. If there's any noise in that feature, then it pretty much has to increase the variance. So the message of those 2 points together is do not add a new feature unless it reduces the bias more than it increases the variance. I will also mention that you can't reduce the irreducible error, which is why it's called the irreducible error. No amount of data sampling is going to change that. Also, just to be clear, if there is noise in the test set, that affects only the irreducible error. It does not affect the bias or variance of the method. Whereas, if there is noise in the training set, well, that affects the bias and the variance of your method, but not the irreducible error. So coming back to what I was talking about a moment ago when I was answering one of your questions, it's worth repeating that we really can't measure the bias or the variance on real-world data. So this isn't an algorithm. This isn't a here's how you train discussion. And the reason why is because we can't know G exactly. We can never know G exactly. Also, our noise model might be wrong. But what we can do is we can test different learning algorithms to see if they work or not, if they make sense or not, by using synthetic data. So when I say synthetic data, I mean you write a computer program that picks G, so you know what the ground truth is, and then you add random noise, so you know what the true noise model is. And then you test your different learning algorithms to see which ones work best on that synthetic data. That gives you some information about what might work best on real-world data. And there is a nice example of this in one of your textbooks. From Introduction to Statistical Learning, we find this example here. Now, what they're doing here on the left is they are fitting splines to data points. So in the figure on the left, you can see there's a black curve here, which is the ground truth curve. And what they've done is they've sampled a bunch of training points off